Section 3.4 talks about parallel and perpendicular lines. The objective for this lesson is to be able to relate parallel and perpendicular theorems. Now remember, parallel lines are two lines that do not intersect and are in the same plane. Perpendicular lines are two lines that intersect in the same plane and form right angles. Okay? So the first theorem that we have is Theorem 3.8. It says if two lines are parallel to the same line, then they must be parallel to each other. So here's what it's saying. You've got two lines. Let's say we have line L and line M. And we know that line L is parallel to line M. L is parallel to M. And we have a second piece of information that says M is also parallel to this other line here called N. So we know that M is also parallel to N. When this occurs, we can conclude that L must also be parallel to N. All right? If two lines are parallel to the same line, both line L and line N are parallel to line M, then they have to be parallel to each other. All right? The second theorem that we have here is Theorem 3.9. It says, in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So let's take a look at what this one's saying. We've got two lines that are perpendicular to the same line. So let's say that we have some line here, L. And we have a line that is perpendicular to line L. We'll call that line M. And we have another line, N, that is also perpendicular to L. So again, let's look at the given information. We're told that L is perpendicular to M and L is perpendicular to N. If this scenario occurs, we can conclude that M is parallel to N. If you look at it, it kind of makes sense because both those right angles there, we're going to prove it in a little bit. But notice both those right angles are corresponding angles. Two lines cut by a transversal, corresponding angles are congruent. The lines have to be parallel. And then we have a third one. This one actually has a name. It's called the perpendicular transversal theorem. It says, in a plane, if a line is perpendicular to one of two parallel lines. So let's try to sketch that out. A line is perpendicular to one of two parallel lines. So we know that we have parallel lines. Let's call the parallel lines L and M. All right, and they are parallel to each other. And then we have this other line. Let's call this line N. And all that we know is N is perpendicular to M. All right, so let's write this out. We've got L parallel to M and N perpendicular to M. When this occurs, we can conclude that N must also be perpendicular to L. And if you look at it, it kind of makes sense. If that's a right angle and these two lines are parallel, then by this transversal cutting it, we know that this angle right here at L also has to be 90 degrees because two parallel lines cut by a transversal, corresponding angles are congruent. That forces N to also be perpendicular to L. All right, so let's look at a couple of problems here, or one problem and a couple of proofs, I should say. A carpenter plans to install molding on the sides and the top of a doorway. So molding is that stuff around the edge of the doorway. The carpenter cuts the ends of the top pieces at one end of each of the side pieces at a 45-degree angle as shown. Will the side pieces of the molding be parallel? All right. So if I look at it, what I'm really looking at is a scenario something like this. That's the top of the door frame. And if I take those two 45s and put them together, I have two right angles there. All right. Now, they want to know, what can you tell me, and I'm going to just use some names here, what can you tell me about L and M? Well, if both of those are 90 degrees when they're formed, I can conclude that L has to be parallel to M, or the side pieces have to be parallel to each other because same side interior angles being supplementary, okay? Or I should have used, even better than that, the converse of same side interior. All right, so I don't like that one. Let's use the converse instead. Converse is what we use to determine that two lines are parallel. Okay, so let's take a look at this proof here. This is a proof of Theorem 3.9. Remember, 3.9 talks about two lines perpendicular to the same line, then they're parallel to each other. All right, so here's our scenario. All right, I'm going to start off by claiming the given. I know that R is perpendicular to T and S is perpendicular to T. I know this to be true because it's given. Now, if I have perpendicularity in this picture right here, I know that I can conclude from perpendicularity that angle 1, the measure of angle 1, is equal to 90, and the measure of angle 2 must also be 90. And the reason why I know that to be true is because of the definition of perpendicular. 90-degree angles have to be formed. Okay, so I've got 90 for angle 1 and 90 for angle 2. Remember, we're trying to prove that the lines themselves are parallel. Well, let's see, what can I do here now? Well, I know that I could simply conclude that R is parallel to S. And the reason why I can conclude that, once I know those angles are 90, I can conclude that they're parallel by the converse. Angle 1 and angle 2 are corresponding. Converse of corresponding angles. That's how I can conclude that they're parallel to each other. All right, and then the last question here says, what if you got a scenario like this? So take a look at it first. It says C is perpendicular to B. Got it? They got it marked on the picture. B is perpendicular to D. Got it? It's marked on the picture there. And D is perpendicular to A. How could I prove that line C would be perpendicular to line A when on our picture they're not even meeting each other? All right, so let's take a look here. Statement number 1, I would go ahead and say that C is perpendicular to B and B is perpendicular to D because it's given. Oh, why do I always want to write a 2 there? So it's given. All right. Because of that, I can conclude that C is parallel to D. All right. If I can conclude that C is parallel to D because of the converse of corresponding angles. All right. Or I could also have said two lines perpendicular to the same line must be parallel. Either one of those reasons will be fine. Okay. But now I know that C is parallel to D. All right. I also know that D is perpendicular to A, and I'm going to state it again, even though I don't need to, that B was perpendicular to D. All right? The reason is that's given. Because I know that these two perpendicularities occur, then I can conclude that A is parallel to B. And the reason for that will be the same thing, converse of corresponding angles theorem, or I'm going to write it down this time, two lines perpendicular to a third line are parallel. All right. So how am I now going to tie these together and try to prove that C is perpendicular to A? What are you thinking? Well, if A is parallel to D and D is parallel to C, or C is parallel to D, I'm kind of stuck here. What do you see? Hopefully you see something. I'm just getting a little bit stuck here. All right. I know I can conclude there it is. Because C is perpendicular to B and A is parallel to B and C is parallel to D, I can conclude here that C has to be perpendicular to A by the last theorem that we talked about. Let me just double check its name. The one that says the perpendicular transversal. If a line is perpendicular to one of two parallel lines, then it has to be perpendicular to the other as well. All right. Oh, I'm a little bit too far. So it's called the perpendicular transversal theorem. All right. Hope this helps. Good luck. Make sure you get the Math Excel assignment completed.